Right, power. So this is chapter 7, numbers 43 to 46. And I'll just remind you here that we know now power, capital P, is equal to the rate at which work is being done with respect to time. So that's dW dt. Now, average power would just be the amount of work done over a time interval. But instantaneous power is this derivative, and we know from our notes that that is equal to force times velocity. So you got to kind of pay attention to what you have and which one of these you should be using. Number 43, we have a force of 5 newtons. It's acting on a mass of 15 kilograms, and that body is initially at rest. So we want to compute the work done by the force in the first, the second, and the third seconds. It's a constant force, so here work is equal to force times distance. They're in the same direction, so I don't need the cosine theta. During the first second means from time 0 to time 1. And we might notice here, since force equals mass times acceleration, the acceleration of this thing is going to be 1/3 meters per second squared, right? So I think I need to know, since I need these displacements, I need to know where it is at time 0. I know it's at position 0. At time 1, well, let's see, so a little bit of kinematics here. It's not very hard kinematics. We know that, let's see, where should I do this? I'll do this right under here. The acceleration is 1/3 of a meter per second. The initial velocity starts from 0. We don't need to know the final velocity. Actually, we might for later part, but I want to know the displacement at various times, and the delta t, or the amount of time that's gone by. So I'm going to do for time 1, 2, and 3. So here, delta x is equal to 1/2 at squared plus initial velocity times time, but the initial velocity is 0, so that term is gone. So the position at each one of these is just 1/2 at squared. So here it's going to be 1/3 of a meter. Oops, sorry, 1/6 of a meter rather, right? 1/2 times the acceleration times t squared when t is 1. When t is 2, then I'll plug that in 1/3 times that, so 1/6 times 2 squared, so that would be 4/6 or 2/3 of a meter. And at time 3, that'd be 1/6 times 3 squared, it's 9, that's 1.5 meters. Right? And they also want to know later what's the instantaneous power at the end of the third second. So that'd be the final velocity at the end of 3 seconds. So let's see, with what we know there, I would know this, this, and this. So at the end of 3 seconds, if it starts from velocity 0 and it has an acceleration of 1/3 of a meter per second, then the velocity at time 3 will be 1 meter per second, right? If it increases by 1/3 of a meter per second every second. So I'm going to need that later for part D. So for part A, work is equal to force times the distance it went in the first second. What started at 0 went to 1/6, so that's 1/6 meter. Newtons times meters is joules, so it'd be 5/6 joules there. The work done in the second, that's between time 1 and time 2, it went from 1/6 to 2/3, or in other words, from 1/6 to 4/6. So it went 3/6 or 1/2 a meter. I'm not using this number because I only want to know how far it went during that time interval. So it went from here to here. So that's 5/2, 2.5 joules. And then the work done in the third second, that's from 2/3 to 1.5. That's a half plus a third, which I think is 5/6. You can check my math there. Sorry if that's not right. So it's 25/6 joules. And then part D, we have, we want to know what's the instantaneous power. Instantaneous power is force times velocity. And the velocity at time 3 is equal to 1. So that's going to be 5 watts. Notice that this is joules per second, right? That's a watt. I'll just give those answers a quick check. Make sure that we're good there. 43, so we have 5/6, 2.5, 4.2, and 5 watts. Good. Cool. Number 44. We've got a skier pulled by a tow rope up a frictionless ski slope that makes an angle of 12 degrees with the horizontal. That's 12 degrees. The rope moves parallel to the slope with a constant speed of 1 meter per second. So we're moving up the slope at 1 meter per second. The force of the rope does 900 joules of work on the skier as the skier moves a distance of 8 meters up the incline. So we have 900 joules of work in 8 meters. And since work is equal to force times distance, it's parallel to the slope, so they are in fact in the same direction. That would be the force from the rope would be 900 divided by 8, which is that 125 maybe? Divided by 8. Oops, not quite. But let's say 113 newtons. If the ropes moved with a constant speed of 2 meters per second, how much work would the force of the rope do on the skier as the skier moved a distance of 8 meters up the incline? Well, if the rope moved with a constant speed of 2 meters per second, the force would be the same. It would still be balancing that force, right? So let's see if we can figure that out. This is the answer for part. Wait, is it an answer for any part? Hold on a second. No, I guess I haven't done anything yet, right? So if the, sorry, we haven't, I thought I answered part A. So part A is if instead the constant velocity was 2 meters per second, well, that's still constant velocity, right? So the force would not be different because it would still be a constant velocity. So it would still be, in fact, the same amount of work because we would still be at a constant velocity. So in that distance, that doesn't really play into this, right? It's still a constant force, so the amount of work would be the same. In part B, at what rate is the force of the rope doing work on the skier in these two situations, if it's going 1 meter per second or 2 meters per second? So power is equal to force times velocity. Excuse me. So in the first part, we have the force is 113 newtons about times the velocity of 1 meter per second. So that's about 113 watts. And in part C, the force would be the same. Did I point to that and say force before? That's work. I'm sorry if I did that. And then 2 meters per second now. So although the force is the same, it would take more power to make it happen at a greater velocity. Right? That's what's happening there. And that's an important thing to realize about power. Number 45, we've got a 100 kilogram block pulled at a constant speed of 5 meters per second. Meters per second across a horizontal floor by an applied force of 122 newtons, directed at 37 degrees above the horizontal. What is the rate at which the force does work on the block? Well, the block's moving this way, so this component of the force, that's the displacement. That's the only part that's doing work. So we have power is equal to work over time, or force times velocity. Since this is a constant force, these two things will be the same. So I think that it'll be easier for us to do this, right? We could do either one, but I think we'd probably have to do a little kinematics, although it wouldn't be very hard. Not even kinematics, just like distance equals rate times time to figure out that time. But I think it's going to be easier for us here. So the force that's in that direction that's the cosine component, right? So looks better if the calculator's on. 122 times the cosine 37 degrees. I'm in degree mode. Now it's about 97.4 newtons times the velocity is 5 meters per second. So times 5, that's about 490 watts. Number 45. So these are pretty, they're not really hard, these power problems, to get a handle. I guess the most confusing thing is knowing which one of those you should use. Last one, number 46. We've got the loaded cab of an elevator has a mass of 3,000 kilograms, and it moves 210 meters. I'll call that delta Y. 210 meters up the shaft in 23 seconds at a constant speed. Now that constant speed here, since it's constant, it's just distance divided by time. So that would be 210 meters over 23 seconds, so about 9.1 meters per second. At what average rate does the force from the cable do work on the cab? If it's going up at a constant velocity, make a quick diagram here. The force of tension from the cable would have to be equal to the force of gravity, right? If it's going up at a constant velocity, those would have to be equal. So the tension force would just be equal to 9.8 meters per second squared times the 3,000 kilograms. And that's about 29,400 newtons of force. And if we're going up at 9.1 meters per second, then power is equal to force times velocity. So that's going to require about 268 kilowatts, right? And the book has that as, not that it matters to you, because it's an even numbered problem. They have 2.7 times 10 to the 5th watts, same thing. Right? So there you go.